we are left with a series of easy, simple properties of symmetric tensors and isotropic functions. I want to start with one technical lemma. In this way, our brain is fresher, okay? But you should not consider this as a difficult object, a difficult theorem, difficult lemma. You may ask help to your geometrical intuition, even if I try to stay algebraic. Okay, so everything can, in general, be generalized in n dimensions. However, we keep having in mind the case of 3 dimensions, and we apply properties in such a way that you can generalize easily to n dimensions. Okay, so we present a theorem which is true in a more general setting. However, for having a grasp of what is happening, we picture our vector space, we imagine our vector space as if it were 3-dimensional. Okay? The most usual applications in continuum mechanics are involving this kind of 3-dimensional spaces. So, in general, this is enough. Okay. So, before repeating another time the representation theorem for scalar isotropic functions, which we proved last time completely, but I think it is better that we repeat it another time. We need to prepare the next and last theorem. Okay, we will stop there, about the representation theorem for tensor-valued functions which are isotropic. So, you have a function which is mapping symmetric tensor S, the symmetric tensor S, into another symmetric tensor. To be isotropic means that for every Q orthogonal, okay, PGS P transposed is equal to PS P transposed. So to be isotropic, it means either you rotate the independent variable and then you apply G. Okay? Or you apply G and then rotate what you have got, the result is the same. Okay? We will go, before concluding this lecture, this course, we will go in deep detail in the description not only of the dissipation density, energy density, which we already treated, but we will also talk about isotropic linear elastic solids. If you have a reference configuration, you can turn the solid and then deform it, okay? Or you deform it and then turn. What we want to say, treating with isotropic constitutive equations, is that the final result is the same. Okay, but we will go in great detail in understanding this. Okay, so when you say that a body has no preferred directions, mathematically you say the constitutive equation verifies this property. If you turn the reference configuration and you deform, Piola stress is turned exactly of the same amount in which you have turned the reference configuration. And this is true for every rotation. Okay? So what you have to understand is that these assumptions, these physical requirements are needed in many different parts of mechanics and not only of mechanics. So when you talk about objectivity of dissipated energy, you need this property. When you need to discuss about isotropy of a solid body, you need this property. Even if the map G is different in the sense that its physical meaning is different. Okay? In the case of solids, the application, the constitutive equation is giving you Piola stress in terms of deformation. In the case of viscous fluids, you are introducing the constitutive equation giving you Navier-Stokes stress as a function of the symmetric part of the gradient of velocity. So the meaning is different, but the two constitutive equations have the same structural property, isotropy. Okay, so I repeat you once more why now we need to invest our intelligence to understand how are made isotropic functions, which is their constitution. So consider a map G mapping symmetric tensors in tensors. Okay? And let us assume it is isotropic. Now, the statement I tell you is very easy to understand, even if it is not so easy to prove. Consider an eigenvector of S relative to the eigenvalue lambda. Okay? Gs of V is equal a given mu times V. So there exists a mu, a real number mu, such that Gs of V is equal mu V. So in words, an eigenvector of S is an eigenvector of Gs. Of course, the eigenvalue changes in general. This is the crucial property of our representation theorems. So it is useless that we rush in listing many results. It is very important that you understand completely and in full detail one part of all this theory, because in this way you have the conceptual tools to understand whatever part you may need in future. So the crucial idea is, the crucial point of all the representation theorems is the following, is exactly this one. If I have a map which takes one symmetric tensor and maps it in the set of linear tensors, okay, if you have an vector of S, this is an eigenvector of the image. So isotropy is preserving the set of eigenvectors. This is the crucial point of all our story. Okay? Now, the trick for proving this lemma is divided in 3 steps, and one intermediate step needs a zoom. We will zoom in it. So I will tell you about a side result which we need. We use this side result and then we will go to prove it. Okay? So in this way you have an idea of the strategy of the proof, and then you get all technical details. Okay? So I told you the physical motivation for which we are interested in isotropic maps. Okay? Then I stated the fundamental property of isotropic functions. You could say in words, isotropic functions are conserving the eigenvectors. Remark that the eigenvalue can change, and in general, indeed, it changes. Okay? Now, we prove this. The trick is the invention of a particular linear map. This particular linear map is the symmetric map, which is reflecting all vectors with respect to a plane. So what we do? We introduce the linear map P symmetric. Okay? There is nothing you have to understand. This is a definition. So you have to understand the definition. You take a linear map which is symmetric. How you define this linear map? We start from this V. So think in your mind a vector. Okay? So consider the space orthogonal to this vector. So the plane which is orthogonal to this vector. PV is minus V. So you are reflecting the V. If you have a vector orthogonal to V, so for every W orthogonal to V, PW equal W. So this P is the identity on the space orthogonal to V, okay? And every vector parallel to V is mapped into minus V. Of course, another vector, if you have a vector which is neither parallel to V nor orthogonal to V, however, this vector will be projected along V and along the plane orthogonal to V. So you can extend this P for every vector once you know, if you assume it is linear, of course, once you know the image of PV and the image of PW. Okay? So there is a unique symmetric linear map which we have called P, such that PV is equal minus V, and such that for every W orthogonal to V, PW equal W. So this is something which you have met 1,000 times. Okay, is the reflection with respect to a plane, the plane orthogonal to V. So the only delicate point is that your V is an eigenvector of S. this is the first step. Now, do you remember the crucial theorem I asked you to read alone? Every symmetric tensor has an eigenbasis constituted by orthonormal vectors. So V is an eigenvector. In the plane orthogonal to V, you have all the other eigenvectors. So if you have the matrix, the linear application symmetric S, you have a set of eigenvectors. The first one is V, then you have E2, E3, E4, En. In our case, if you are in 3 dimensions, you have V, E2, E3. Okay, and E2 and E3 are orthogonal to V, so they are W's such that W dot V equal to 0. So what happens to each of these eigenvectors? P of V is equal to minus V. P of E2 is equal to E2, and P of E3 is equal to E3, by definition. So we can tell the following thing. Given the eigenspace relative to any eigenvalue lambda, P of this eigenspace is included in the same eigenspace. So what is doing this P? It is preserving the eigenspaces of S. So this P is a linear symmetric map which takes an eigenvector of S and maps this eigenvector in another eigenvector of S relative to the same eigenvalue. Okay? Now, you have to believe, we will do the calculations later, you have to believe the following fundamental, the validity, that it is true, the following fundamental spectral property. If you have a symmetric linear map which is mapping a given eigenspace into itself, then this operator is commuting with the operator S, which we have at the beginning. Okay, maybe I have to underline this point. In general, when you have the composition of linear maps, this composition is not commutative. I hope that you have clearly in mind this. So if you have this can be seen easily in linear algebra when you try to multiply row times columns, 2 matrices, and you discover that the order is important. So commutation of 2 linear applications in general is not possible. What we have proven now is that given an eigenvector V and considered the projection, the reflection with respect to the orthogonal space, the orthogonal plane to V, what we have called P, the linear operator P, okay? S and P actually commute. And this commutation rule is easily obtained. We need 3 lines of calculations, but it is easy. You simply need to do some algebraic calculations. This is easily seen when you remark that P is mapping every vector in the space of eigenvectors relative to lambda in the same space of eigenvector relative to lambda. Okay? So we can use, we will prove this later, we can use the commutation rule. Okay. Now we are ready to prove the theorem. So this is a definition and this is a fundamental result which is preliminary. So there is a peculiarity. This animal is orthogonal. It is a reflection. Okay? So the P which we have introduced belongs to the set of orthogonal matrices which are in the set of invariant rotations for our isotropic function. So P, now this P is exactly this P here. Okay? P GS P transposed is equal, because of isotropy, to G P S P transposed. Okay? And this is equal to GS. Now, how we prove this? You calculate P GS of V. So, this is a vector. G of S is a matrix, a linear application. You apply to a vector, you get another vector. Then you have P applied to GS of V. So at the end, you have a vector. However, P and G are commuting because of this. So Pg of S is equal to GS PV. So the isotropic assumption implies that P is commuting with G. Okay? I see you a little bit surprised, but if you consider that apply 2 times P, P squared is equal to V. So P squared is the identity. So P is at the same time symmetric and orthogonal. Okay? So you take a vector, P transposed is equal to P, so you have minus, you apply S, then you apply P, you get another minus, so this is the reason for which you have this equality. Okay? course, P and S are commuting. So here I jumped a passage. So you have PS equal to SP. And then you have P transpose, which is the identity. Okay, so this is due to the isotropy, and this is because of 2. Okay? So I try to go slowly to tell all details. Okay? So we need to use the ingredient. The ingredient, the hypothesis. The hypothesis is G is isotropic. G is isotropic means that this animal is equal to that animal. Then, because of the definition of P, and because of the commutativity rule, SP is equal to PS, so you have a commutation, and therefore you jump from here to there. Then you remark that P transposed is equal to the inverse of P, and it is equal to P also. So this linear application is equal to S. This line, if you multiply times P on the right, implies the commutation. So this is equal to that, because from this equality you multiply times P on the right, you get PG equal GP. Okay? So there is nothing difficult. The only strange thing, I mean, this is not algebra of high school, simply because you are handling with non-commutative product. So when you want to commute the factors of a product, you need to be sure that you can do it. Okay, otherwise this is simple, very simple algebra. Okay, so PGV is equal to GPV. Okay. And then PV is equal minus V. Okay. So you discover this interesting thing. P applied to a vector is equal to minus that vector. Okay. How you have built P? You have built P in such a way that it is changing the sign to every vector parallel to V, and it is leaving not changed every vector orthogonal to V. So we must conclude that you have a mu such that GSV is equal mu V. So the only fact to have an isotropic function mapping linear symmetric tensors in linear tensors, only the requirement of isotropy implies that the set of eigenvectors remains unchanged. So think about the importance of these applications. If you have a constitutive equation mapping the formation of a solid into Piola stress you know that every eigenvector of deformation, if you have an isotropic material, is an eigenvector of stress. And if you have an eigenvector of the symmetric part of gradient of velocity, you have that this eigenvector is an eigenvector of Navier-Stokes dissipation stress. So isotropic constitutive equations are not changing the set of eigenvectors. Okay, so in order to be sure that what we have done is true, we need to prove the commutation rule. So we do it. This is very easy. You need simply to calculate. Of course, you once more, also in this other proof, you will need to assume the representation theorem for every symmetric tensor. So the fundamental ingredient of all these theorems is the possibility of finding a basis of eigenvectors for a given symmetric tensor. But this is an old story. You cannot do very much in solid mechanics, in Lagrangian. When you talk about the distribution of mass in a region, if you study the rigid body motion and you look for the principal directions of the mass tensor, okay, for the kinetic energy, for instance, you use that it is symmetric, and then you find the particular tripole of axes in which the kinetic energy is diagonal. So you find very often the need of discovering eigenvectors and eigenvalues for a symmetric tensor. You already did without maybe remarking it explicitly. Okay, so what we need to prove? If A is symmetric and B of E lambda is included to E lambda, where E lambda is the set of eigenvectors for A relative to lambda. So if B is mapping E lambda inside E lambda, then B and A are commuting. Okay, we need to prove this. So the idea is the following. And this is a simple calculation. So the trick is, take a vector U, you decompose it where? Exactly in the eigenbasis of A. So you decompose it as sum over alpha I Vi, where Vi no sum. Okay? So I know this assumption is used so often that at the end you believe it is always possible. So I want to underline, we can do this decomposition in terms of eigenvectors relative to the matrix linear application A is possible. So every vector can be represented in this way only because we know there is a basis of eigenvectors. And we know that there is a basis of eigenvectors because A is symmetric. So, without a theorem of existence of a basis of eigenvectors, all these reasonings are impossible. So, this is the reason for which all mathematics of 20th century is, or a great part of mathematics of 20th century was directed towards the study of spectral properties of linear applications. When you have enough eigenvalues and enough eigenvectors to span the whole space where you are living, your life is easier. If you don't have enough eigenvectors, you are lost. Okay, so what I'm telling you, I am telling you a story about finite dimensional vector spaces and symmetric tensors. So we fly in a very low level mathematical theory because this is very simple, purely algebraic. However, when you want to develop numerical methods in which your space, your vector space is infinite dimensional and your linear operator is self-adjoint, which is the generalization in infinite dimensions of the symmetric tensors, then your problem will be, I want to repeat all these calculations. So I need to understand in deep detail how the set of eigenvectors and the set of eigenvalues are constructed in this more general setting. So not only what I'm telling you now is important by itself, because in this way you learn how to find the correct constitutive equations in your models, especially if they are isotropic. But also I give you some ideas on how more general theories are to be developed. Okay, so I know that for the particular symmetric tensor I have, this representation is possible. Now on calculations. So it's very easy because what I have to do, I write A, B, U equal sum over I, alpha I, A, B, U, I. Okay? Now, A, B, B, VI. Now, let us do this calculation on a side. A, B, VI. We know that BVI is an element of the same eigenspace. So, by hypothesis, ABVI is equal to lambda I BVI. Okay? So this is our assumption. If VI is an eigenvector of A, then BVI is an eigenvector of A relative to the same eigenvalue. So this is the assumption. So I have written that BVI is an eigenvector of A. Okay? So this is equal to B lambda I VI, okay, and lambda I VI is equal to A VI. So what I have written? I have written the commutation rule between A and B in the particular case of eigenvectors of A. Okay? Now, I remember that I needed all this stuff for studying quantum mechanics. This is a crucial point in quantum mechanics. When two linear maps are not commuting, you have some quantistic rules. The amount of non-commutativity gives you the discrete amount of energy which can be exchanged between a system and the exterior world. So when you have commutation rules, you have no quantum exchanges, and when you have non-commutativity, you have quantum exchanges. Okay, but in this moment, I want to underline that this is simple algebra, and this means that the commutation of A and B is possible on eigenvectors. Now, ABU is equal to this. I apply the commutation rule to the eigenvectors. Okay. And as everything is linear, this goes inside, and so we have the commutation rule for every vector u. Okay? So I want to underline that all these may seem a very abstract story. However, if you zoom in all details, everything is simple. I mean, I like very much the image given by Whitehead about mathematics. Mathematics is like a big pyramid. You are far, you see a huge construction, and you are frightened. But if you go close, you see that the same stone, repeated million times, placed one on the other with method, allows you to build the pyramid. So there is nothing complicated. There are some fundamental ingredients. In this context, this decomposition is possible with eigenvectors, and this is possible because A is symmetric. Okay? And the invariance under B, which is your assumption, under the invariance under B of the set of eigenvectors. Okay. Now, we will decide how to proceed next. I want to repeat now the last theorem of the last lecture, because we need it for continuing. I believe that in the last time it was maybe my fault, because the theorem is done. There is no difficulty. Look, given a symmetric tensor, by the way, in all books of classical mechanics, engineering mechanics, strength of materials, everywhere, every symmetric tensor is very often confused with 3 eigenvalues and the corresponding 3 eigenvectors. I'm sure you have heard 1,000 times talking about principal directions of stress, principal direction of kinetic energy tensor, principal directions of strain. Actually, taken a symmetric tensor S, you can find lambda 1, lambda n, E1, En. Lambda 1, lambda n are the eigenvalues, E1, En are the eigenvectors. You can have repetitions. Okay? However, in lambdas, you cannot have repetition in i's, because this must be a basis of your vector space. So, given a symmetric tensor, there is a unique choice of lambdas and e's, which are the eigenvectors and the eigenvalues for S. Vice versa, given lambda 1, lambda n, E1, En, you can build in a unique way a symmetric tensor having exactly these eigenvalues and these eigenvectors. Now we are very powerful. We have the wonderful tensorial notation, which allows us to write this very easily. Okay? So, you have a 1-to-1 correspondence between eigenvectors and eigenvalues and symmetric tensors. Okay? Now, what we have proven last time in the last lecture, we want to find a scalar function phi of A. So A is a symmetric tensor, phi of A is a real number, and we want to prove that isotropy of phi of A implies that phi of A is equal to phi bar of the invariance of A only. So, if you want to rewrite in a more explicit way, in this way. So, what really is important in our function are only the invariants. Okay? Now, instead of writing phi of A, can I write phi of lambda I, comma EI? It is equivalent. Instead of fixing S, I can fix lambda I and EI. Okay? So what we have proven last time? Last time we have proven that a function phi I constructed in this way is isotropic, because these three animals are objective. Then we assume that the function phi is isotropic, and we want to prove that actually this phi is made in this way. So the only problem we have now is the following. We have to represent this is isotropy. Okay? Given S, we need to represent Q as Q transpose. The calculations we have done, maybe we can repeat them, led us to this conclusion. If you consider S and you consider its rotation, the eigenvalues are the same. So lambda I and lambda I in this representation formula are the same. What happens to eigenvectors? The eigenvectors of this animal are the rotation of the eigenvectors of this animal. Okay? So, either, this has been done for centuries. You can treat a symmetric tensor either as a tensor or as a table. Lambda 1, lambda 2, lambda n, E1, E2, En. So the set of eigenvalues of eigenvectors are uniquely characterizing the symmetric tensor. Now the trick is clear. Isotropy is stating that phi lambda I EI is equal, which is phi. With abuse of notation, I am writing the same phi for the phi mapping S and phi mapping lambda I EI, okay, as independent variables. So phi S is equal to this, but it is also equal to this animal. Okay, but we know that this is equal to phi of lambda I, because lambda i's are the same, comma, QEI. And this equality is true for every Q. Now, the game is over, because you have that phi lambda I EI equal to phi lambda I Q EI for every Q. And this means that this phi cannot depend on the vectors. Because for every basis, you can go from one basis to another one using a suitable Q. So, phi lambda I has the same value on EI and on any other QEI. So it is independent of the vectors. So the end of the game is that a scalar function, which is isotropic, can depend only on the eigenvalues. We have already seen that the eigenvalues are the roots of a polynomial in which the invariants are the coefficients. So either you know the eigenvalues or you know the invariance. So you can find always a change of variable, and you can, instead of considering eigenvalues, you can consider the invariance. So this is the story. Okay, now let us see what time is it. So maybe we can do the following. I can state the next theorem, which we prove next time, and then we talk a little bit about the importance, the historical importance, and the practical importance of the result we are talking about. Because even if you may not perceive it, but this theory is behind the engineering practice which is ruling the industry of concrete, for instance. The big controversy which started between Lamé, Navier, Poisson was very violent, because they did not manage easily to understand how is possible to construct the most general isotropic function. So how many Lamé coefficients may exist? Somebody said 1, somebody said 2, somebody said 3. Okay. Now we will discover that in linear elasticity there are only 2 Lamé coefficients. However, if you have a rubber, so an isotropic material which is nonlinear, how many coefficients do you need for characterizing that, for instance, cubic, quadratic, quartic rubber? The theorem which we have proven and the theorem which we will prove next allow you to characterize every constitutive class of materials if it is isotropic. And this was the beginning of all the theories of classification. Okay? Okay, now let us consider a map Y taking every symmetric tensor into another symmetric tensor. So while previously we considered scalar valued functions, now our map is from symmetric tensors to symmetric tensors. So instead of talking about energy, we are now talking about stress, for instance. Okay? Now, we already said what it means that this function is isotropic. And we have proven a preliminary lemma about this class of function. We said that every eigenvector of V is an eigenvector of Y of V. Okay? Now, I am not so sure, but in the literature they claim that this theorem is due to Rivlin and Eriksen. But maybe they are not the first ones, but anyway. Y isotropic implies that Y of V has this particular form. You may believe it is too simple, even. Every isotropic map which maps symmetric into symmetric tensors can be represented as a scalar function of the invariance of V times the identity plus another scalar function of the same invariance times V plus a third scalar function times V squared. So you can understand that isotropy is limiting a lot the possible constitutive equations. In the enormous world of functions, you fall in this very limited class. Okay, now it is clear and trivial, we do it immediately. It is trivial to see that this is isotropic. Why? Scalar is a scalar. Scalar of invariance is already isotropic. Okay, so if we consider QVQ transposed, this animal remains unchanged, this animal remains unchanged, this animal remains unchanged, okay? So, we simply need to understand what happens to Y of it's much better. We do the calculations and that's it. Y of QV Q transposed is equal to V0 times identity. This is invariant. Plus V1, which is invariant. Instead of V, I have to consider Q, V, Q transposed. Okay? Plus V2, I have Q, V, Q transposed, Q, V, Q transposed. Okay? Then, these two gives you 1. Okay? Then, Q transpose Q is equal 1. So I can write this way. Okay? Then I can factor left Q, right Q transposed, and I am left with Q Y of V Q transposed. So it is clear that this structure is a good one. I mean, at least it is surely isotropic. What will need some detailed calculations in the same spirit of the calculations we have done before. Will be the proof of the vice versa. I mean, to prove that every isotropic function can be represented in this way will require some time. Okay? Okay. So we have proven one half of the theorem. Next time we prove the remaining half. Now let us discuss a little bit about preliminary considerations about Lamé coefficients. So we understand how we will conclude our course. Now, how many coefficients do we need for a linear constitutive equation which is isotropic? So we have this general structure. V0 is a generic function of the invariance. V1 is a generic function of the invariance. V2 is a generic function of the invariance. So now what we have to understand is what we mean with linearized theories. I don't know how familiar you are with this concept. So let us start with what we have called green deformation tensor F transpose F. You remember this animal is measuring the deformation of a solid. Okay, what we mean with linearized theory? This is a delicate point and I want to be sharp. For some reason, engineers declare that linearized theories are more practical and you can understand them better. I'm sorry, I know I'm not an engineer, but I don't believe that it is easier to understand better linearized theories. If you have a beam which is turning around a rotation axis of an angle theta, and you assume that this beam is rigid, I mean its length is fixed, okay, you can grasp the finite rotation of this very easily. If you write the rigid body motion velocity field, you get a linearly dependent arrows. This is the velocity field in the rigid body motion, and the length of this animal is bigger than the length of this animal. Why it is more physical? It's less physical. Why this length is different from the other one? Because you have a quantity and you are developing this quantity in a Taylor series, and you are truncating this series at the first order. So what happens is that the difference between this length and this length is an infinitesimal of higher order than the first. So actually, linearized theories are a mathematical trick without any physical content. You will never perceive linearized theory with your intuition. You perceive finite theories with your intuition. And this is proven by what? This tensor has been introduced by Green before its linearized form. So if a linearized form is simpler, why it is invented after? So actually what is very crazy sometimes with practical engineering is that you are confusing what is practical for doing calculations with what is understandable. Now, why we want to linearize? That's clear. We want to write linear equations. So, linear equations are easier to solve, so we want to truncate every Taylor series at the first order, so we can survive better. So, let us imagine our map from reference configurations to actual configuration. We write k of capital X equal capital X plus epsilon u of capital X, where epsilon is a small number. Now we write all equations, including this one. We'll do it next lecture. We write all equations in terms of epsilon. We develop Taylor series in this epsilon, and we kill every epsilon square, epsilon cube, and so on. And we leave only epsilon linear term. So we find so-called linearized theories. So F is equal grad k. So it is 1, the grad capital X is the identity, plus epsilon grad u. this is exact. Then I want to calculate F transposed. F transposed is the identity plus epsilon grad U transposed. Okay? Then I calculate F transposed F. So what I have? I have identity plus epsilon grad U times identity plus epsilon grad U transposed. This is algebra. So I write 1 times 1 equal 1. Of course, this is not one real number, this is one identity. Plus epsilon grad U identity. Then I have identity plus times epsilon grad U transposed. And then I have epsilon square grad U transposed. Okay? So, green deformation tensor is the identity plus epsilon times the double of the symmetric part of grad U plus epsilon square grad U transposed. Okay? Now, if I can neglect so-called geometrical non-linearities, so if I can neglect epsilon squared there, green deformation measure reduces to the symmetric part of grad U. Because 2 times 1/2 is the same stuff. Okay? So now you are starting to understand where we will go. Because instead of C, we can write C nearly equal to identity plus epsilon H, where H is grad U plus grad U transposed. And in our constitutive equation for deformation energy, for instance, instead of C, we can use H, epsilon H. So, what we will do next? We take the general constitutive equation for isotropic solids and we linearize it. So we develop it in terms of Taylor series and we kill everything which is epsilon square, epsilon cube and so on. And we remain only with the linear part. What we will discover? Only 2 coefficients are needed for every isotropic tensor function. So if you want to study linear elasticity of isotropic solids, you need 2 Lamé coefficients. If you want to study the viscous flow of a Stokes-Navier fluid, you need to introduce 2 Stokes-Navier coefficients. Okay? Do you want to consider higher order corrections? You have a rule for finding the number of parameters which you need to introduce for describing higher order effects. Okay? So you have a guide for finding this stuff. By the way, I want to tell you that the poor Navier tried to get the same results starting from a microscopic model. So he took his body, he imagined to have a network of springs connecting point masses, and he tried to find the deformation energy or stress tensor at the macroscopic level in terms of the values of the springs, and he decided that one spring was enough. So he was finding constitutive equations depending on one parameter only. So no Poisson effect. In Navier theory, you pull a material and the lateral, the section of, in the transversal direction of the deform elongation, okay, can be deformed in a unique way. So you have only one determination for Poisson coefficient, which is physically inconsistent. So at the end, this theory is due to Lamy. Of course, we did it in, we will do it, we did it in 2 lectures, we will do another lecture. So 4 hours about, okay. The poor Lamy needed 100 pages because he had no tensors, no linear algebra, so he needed to build all results by hand, rather painfully. Okay? Okay, so we meet.